So I forgot to say, in higher derivative theories with the Feynman prescription, you can prove this thing. Instead, we will see there is another prescription where instead of having plus or minus 1 in between, you have 1 or 0. And the zeros can be thrown away. And that is when the projection works. But for that, you need to change the prescription. And to understand what you have to do, we need to study what happens in loop diagrams, because, as we said, we cannot project away things from in and out states because they will be regenerated in loop diagrams. And the reason is that the equation here is quadratic, not linear, and therefore it mixes different orders of h bar. So h bar is one loop, that is h bar squared, so on and so forth. So two loop, one loop, three level, they mix with one another, which means that a projection of the in and out states, which is a three-level thing, cannot be consistent unless it's checked that it is consistent with what you get from loop corrections. And the simplest case we can consider is the bubble diagram, where the optical theorem tells you that this, the imaginary part, twice the imaginary part of minus I, the bubble diagram, is given, basically the identity tells you that the, you see, is T dagger T. That can be expressed diagrammatically in terms of what's known as a cut diagram, which you take the diagram and you cut in two. It's a little bit more complicated, but basically what you get is, take the diagram, cut it in two, you have these vertices. On the left you have this, on the right you have that, and the cut tells you that one side is the complex conjugate of the other. And then you have to integrate on the phase space of final states, which can be written, well, the integral is a complicated measure, which you might know from theoretical physics. Anyway, it's something non-negative. That is a cross-section in this case. The imaginary part of the diagram is a cross-section, and it corresponds to a physical process where the initial particle, which in this case is assumed to be equal to the final one, so that's why you have the modulus squared, otherwise you don't have a modulus squared, but you assume that the initial particle is the same, coincides with the final one. You have so final F is final on the right hand side, but it is not final, it's intermediate in the left hand side. So in the diagram, when you compute the diagram, we'll see in a moment, there is a possibility of having the initial particle decay into two physical, not virtual, intermediate particles. That's where the contribution to the imaginary part comes from. And that is indeed a violation of analyticity. It's better to see it explicitly than phrasing it in words. So we consider the bubble diagram. So let's say that we have an external momentum P. So that is K minus P. And for the moment, we study the loop integral without a prescription. because we want to see what the prescription does and how we can change it. So I define this S of k, maybe I do it here, S of k. So this is a normal theory, no higher derivatives for the moment. So this is an exercise that should be found everywhere in textbooks, but it's not found with this detail that we need. So this is equal to P0 squared minus S of k, I wrote S of P. P0 squared minus space components of P squared minus M squared. And that can also be written as P0 squared minus omega squared, where omega is the square root space P squared plus M squared. And that can also be written as 1 divided by 2 omega, 1 divided by P0 minus omega, minus 1 divided by P0 plus omega. This integral we define as m of p. It's amplitude. It depends on an external momentum p, and k is the loop momentum. We will ask ourselves where this function m of p is analytic, and it will be not analytic only when the external particle can produce the internal particle, not as virtual ones, but real ones. So the unitarity, the places where the amplitude is non-analytic tell you about a physical process that's possible, that can occur. Normally we complexify the momenta, particularly the external momentum, but we will complexify also the loop momentum. Many times we will complexify, you can find only the energy to be complexified. We will need to complexify everything, the energy and the space momentum. So most of the time we will, it's enough to assume that the energy P0 or K are complexified, but we will see in a moment that that's not the whole story. So P0 will belong to complex values. P will belong to real values because it's external, so that we can do, and it can be taken to be fixed. But K will belong to complex values. So the loop momentum have to be ready to be considered complex with all their components. So you can ask yourself if this is an analytic function of P. Actually, it's a function of P squared in the end. So that's why you just need one complex component for the external for momentum. Anyway, if you plot the propagator in the complex P0 plane, so let's assume that you have a plane where you have the real part of P0 as x coordinates and the imaginary part of P0. Then S of P has two poles, these two poles, and one will be for P0 real. So if space P is real, omega is real, positive actually. We assume that the square root is positive, so one pole will be here and one pole will be there. Somewhere. When you compute the bubble diagram M of P, so this is this picture is for the propagator. Which is the simplest amplitude, if you want. But now we want the same for the bubble diagram. And now you have two propagators. So the poles are those of the first propagator and those of the second propagator. So in the first case, you will have k0 equal to plus or minus omega of k. Let me call this omega with the subscript to specify its own momentum. Here it is omega of p. So there it will be omega of k. And those two poles are somewhere there. Now we are plotting the poles in the complex k0 plane, because now we refer, for reasons that will become clear, to the complexified loop energy. So the poles of S of k do not depend on P. Their positions are similar to the positions we found there. But then you have two other poles that depend on P, and they are obtained by replacing k with k minus P here. So instead of k0, you have k0 minus P0, and that will be plus or minus omega of k minus P. Or k0 equals P0 plus or minus omega of k minus P. So where are these poles? For the moment, we assume that both k, space k and P are real, but P0 can be complex, so basically there are two pairs of poles that for P equals 0 they are here, but if P0 changes, they move along this, but if P0 is complex, they can migrate everywhere. So let's assume for the moment that P0 and P space are real. Then they can move only on the real axis. They can delete by this P, but for example, they could be here. One here and one there. because in the end the external momenta will have to be real, but we want to study them in a complexified framework. So how to calculate this integral? Because we have to integrate on k0, the loop space momentum, which means that you have to integrate there. And the integral on the real axis is singular in 4 points. The Feynman prescription tells you one way to calculate the integral. Because there you have p squared minus m squared plus I epsilon. So the Feynman prescription is like saying that the mass has a squared mass, has a small negative imaginary part. And that reflects on the omegas, because omega of p, which is this integral, becomes what? Omega minus I epsilon prime, actually. Because if you replace m squared with m squared minus I epsilon, and you expand, because this is just a very small contribution, you will have that. And so if you study the poles of the propagator S of p, which I recall were p0, okay, this we didn't write, p0 was equal to plus or minus omega of p, those becomes plus or minus omega of p minus or plus some small imaginary part. So the pole on the real axis, they are not on the real axis anymore. And you learn that when the real part is positive, the imaginary part is negative, and vice versa. So that is what you get, two poles like this. After that, you can integrate on the real axis with no problem using the residue theorem, but we are not integrating here because it's at 3 levels, so we have to move to the bubble diagram at least to see what happens. So in the case of the bubble diagram, the poles are written here, so k0 is equal to minus plus omega k plus or minus I epsilon prime, and that means they are somewhere there. Yes. And the other pole was k0 equal p0 plus or minus, etc. K0 equals P0 plus or minus omega K minus P, or minus plus here, minus plus I epsilon second. It's not even the same. It's not related to epsilon the same way. So the two poles are basically the same pair of poles here, but then it can be translated, it can be dilated. But as long as the external momentum components are real, then this is the only imaginary part. So the basic structure would be the same. For example, you can have them here. That's an example. So, sorry. One is up, and the other one is down. They can move in their complex plane, but if P0 and space P are real, they can only translate and become actually more distant or close to each other. So now you know how to compute the integral here on K0 by means of the residue theorem. For example, if you have to integrate here, you can close the integration path like that, and you pick those two residues, or the other side, it will give the same result, of course, and you will pick the other two. But the integral on the energy now is done, it's well defined. So that's what the Feynman prescription does. It defines this integral. Actually, it does much more, because it will also define the integral, the remaining integral on the space components. After the integral on the energy, we have to do the integral on the space components. However, there is a thing that can be used to already spot where let's say problems with analyticity hold. Now you know that in complex analysis you can deform the integration path as you wish, as long as you do not cross poles. So for example, instead of integrating on the real axis, I could integrate on this. And what happens is that the following thing, that sooner or later, actually later, at the end, you will have to take these epsilons to 0. And so when you take those epsilons to 0, the poles move to the real axis. What happens then? Which means epsilon going to 0. You have something like this. And where is the integration path? Well, the integration path is the real axis. So when this pole goes down, that means that you have to deform the integration path so as to avoid the conflict here. And with the first red one is the same. with the second blue one is the opposite, and with the second red one is the opposite. Okay, so you can move around epsilon. You can that moves the poles on the complex plane, but you do not have any problem with analyticity because you can avoid the contact between the poles and the integration path. But there is one case where you cannot avoid that. Check this, 2 poles. The red ones depend on P0, the blue ones are fixed. There is a case where they are arbitrarily close, and in that case your integration path will have to be squeezed between them. In that limit, there is no way to avoid singularity, and that's where you have the violation of analyticity. This is called pinching singularity. So the red one moves depending on P0, the blue one doesn't. The 2 poles from opposite side pinch the integration path. It's called pinching, or pinching singularity, whatever, pinching. And you can compute when that happens because it's the coincidence of the 2 poles. The right one of the propagator with no P, so the right one of this with the left one of that. So the right one is K0. We can forget about the epsilons now because they have been taken to 0. So the right one is K0 equals omega K. And the left one is K0 equals to P0 minus omega of K minus P. When you combine the 2, you have P0 is omega K plus omega K minus P. And that's precisely the energy conservation of the process in which P, the external particle, goes into the 2 of the bubble. P goes into K and K minus P. P, so this was the other one, huh? K, this is K minus P. So when that physical process occurs, you have a singularity. And that's where the integral tells you about this possibility of something virtual becoming real, which is what matters in the unitarity equation. You have another pinching when this pair shifts to the left something like that. So when these 2 tend to epsilon tends to 0, they pinch the real axis, and that is another pinching, yes. And that's the opposite. So P0, the energy of the external particle can be positive or negative, depending on whether it is antiparticle or particle. So that's the pinching. You have no problem instead when two poles coincide on the same side of the integration path, when this coincides with this one. That's a double pole, and you know how to apply the residue theorem with a double pole. That's not a problem. No violation of analyticity in the other cases. So that's very important, because you see the magic of this prescription. P0 is a sum of frequencies, or a difference of frequencies. Cannot be frequency minus a frequency, which would be unbounded from below. That would be an instability, because you would have processes where you can generate from any amount, finite amount of energy. You can have an arbitrary, it would have no threshold, because you could always balance that by means of a positive frequency and a negative frequency. You cannot do that. Okay, this is the description. You can be seen explicitly by working out the residue theorem and applying it to this integral. In the end, it is a rational function, so there are 4 poles, 2, 2, and that's not particularly difficult, because S of P, you write it like that. Let's see if we can do it. Yeah, at least we start. We are still in the normal theory here. So that's not quantum gravity, it's just a normal theory. So M of P will be the integral first on the energy, then on the space momentum, and we will have the propagators. The propagators are, we can write them like that, and we do not need the epsilon now, because we know how to surround the poles. So we know that when we will close the integral there, we will just have the 2 left poles or the 2 right poles, depending on where you close the integral. When you apply the residue theorems, you either pick the 2 left poles, or the 2 propagators, or the 2 right poles. And the difference will just be a minus sign that will, in the end, in the residue theorem, will give the same result. We will not be interested very much in the overall constant, so that we can even forget about. So 1 divided by 2 omega k, 2 omega k minus p, and we will have 1 divided by k0 minus omega k minus 1 divided by k0 plus omega k, and that will multiply 1 divided by k0 minus p0 minus omega k minus p, minus 1 divided by k0 minus p0 plus omega of k minus p. So the residues are in the left or both the left poles or the right poles. Let's pick up the right ones. We do not care about the sign, the 2 pi I or whatever, but you can make everything precise if you want. So the two right poles will give the same contribution, by the way. So what you get is d3 of k 2 pi cube 1 divided by 2 omega k 2 omega k minus p, and then you can compute the residue for k0 equal to omega k, or the two right poles are k0 equal omega k or k0 equal the opposite of that. So it's either this or that. So what is the residue on this pole? You just take that and you compute it for k0 equal omega k. And what is the residue on this pole? You just take that, you compute it for the other thing. So let's compute this for k0 equal omega k. And you have 1 divided by omega k. And you see the singularities we anticipated. Okay, this is no singularity for a reason we will see. And k0 equal omega k. Yes. Okay. I think it's better so this is one pole. So we have computed this. No, we have computed that for k0 equal omega k. Then you have to add the other residue, which is this computed for the thing here, k0 equal to p0, no, this thing here, p0 plus, So 1 divided p0 plus omega k minus p minus omega k minus 1 divided by k0 must be equal to p0 plus omega k minus p plus omega k. Okay. Now you see that those with the differences of frequencies cancel out. There is no singularity there. And you remain just with those two contributions with the right singularities, with sums or two frequencies multiplied both by the same sign. And so you have still proportional to, let's forget about the factors, which are not important here, integral d3k 2 pi cube 1 divided by omega k minus p, and then you have Now the sum of two contributions, P0 minus, you can rearrange the sign, minus omega k minus omega k minus p minus 1 over P0 plus omega k plus omega k minus p. So those are the two singularities. So the okay. So the result is analytic everywhere. M of p is analytic everywhere, but where this is singular. And for this to be singular, it's enough to have even one value of k on R3 that makes it singular. So to find the singularities, we have to plot the solutions of this denominator being equal to 0 for every k. But that's quite simple, actually, because we have already written solution. Where was it? The pinching. Here it is. This or the opposite one, Let's write it. P0. So the two cases are with P0 positive or negative. Plus square root of P minus K squared plus M squared. And K spans R3. But you know that this is first, they are real, positive and negative. P0 is real, positive or negative. Second, it goes from a minimum, which is 2m, to infinity. So this is the location of the singularities, which are the branch cuts, two branch cuts. And we can leave it there for today.